wanted to just start with the next section of our respiratory lecture, and this is about, actually we're going to start talking about how carbon dioxide is carried in the blood. So we need to do a little chemistry first, and the first thing is to look up in your notes, see if you can figure out the correct equation for the carbonic acid equation. And you should be able to find that in your notes. If you look it up, you might just pause the video and take a peek at it. But I will tell you now, if you want to stop first, and then you can hear me. Okay, I'm going to tell you. Here it is. C is the correct one. It's H2O plus CO2, and then the enzyme carbonic anhydrase. It's the enzyme that catalyzes this reaction to form this molecule, which is called carbonic acid. And then carbonic acid will just turn right around and break down into the hydrogen ion and the bicarbonate ion right here, HCO3 minus. So we have two ions formed from carbonic acid. We have the positive ion, cation, hydrogen ion, and then we've got the negative ion, also called the anion, the bicarbonate ion. All right, this diagram is kind of important, and this is showing us how CO2 is carried. So imagine that there's a red blood cell floating around in plasma. Here's the plasma. And CO2, let's say CO2 gets into your bloodstream, and it is then diffusing into your bloodstream. 7% will remain, and it will stay and be carried as dissolved CO2. Dissolved in the plasma, but 97% will then diffuse into the red blood cells. Once it's in the red blood cells, about 23% will bind to hemoglobin, forming a molecule called carbaminohemoglobin, which is really just hemoglobin with CO2 attached to it. So we just usually write it as HB with a little line and then CO2. Just so you know, my little HGB in my notes is hemoglobin, and here in the book it says HB. So hemoglobin is the same thing, HGB or HB. Okay, so the 70% though is converted to H2CO3, which is carbonic acid, by the enzyme carbonic anhydrase. And then we know that H2CO3, carbonic acid, will dissociate or break down into hydrogen ions and bicarbonate ions. Now the hydrogen ions will be removed by buffers, especially hemoglobin. Remember, proteins can act as buffers. They can actually pick up hydrogen ions or other ions, and so hemoglobin will pick up the hydrogen ions, and the bicarbonate ion will actually diffuse out of the red blood cell by means of a little transporter, and it moves out of the red blood cell in exchange for the chloride ion. And the reason there has to be an exchange is that when you lose a negative ion from the cell, you're going to make you'll affect the ionic balance. You're going to start to have you'll lose too many negative charges, and so we have to put a negative charged ion back into the cell. So chloride ion comes in, bicarbonate moves out, and this is called the chloride shift. Okay, so just make a note, you do need to know about the chloride shift. Okay, so let's just look at carbon dioxide transport. Some of this is review, we just talked about it. CO2 is transported in three forms, either as dissolved CO2, as carbaminohemoglobin, or as carbonic acid and bicarbonate. So again, the dissolved CO2 is about 7% of your total CO2. So we notice that CO2 is actually much more soluble in water than oxygen is, where I believe only 2% of total oxygen was dissolved. Okay, CO2 can be carried as carbaminohemoglobin attached to hemoglobin. That's about 23% of your CO2. And then it can be carried as carbonic acid and the bicarbonate ion, and that's about 70% of your total CO2 will be carried in this way. So that's worth remembering. Now, carbonic acid and bicarbonate are produced in red blood cells because of the carbonic anhydrase enzyme, which catalyzes this reaction. Again, here it is again. Pardon me because I didn't make the 2's little like they should be. I just kind of typed them in there really fast, so please forgive me. But CO2 plus H2O with the help of carbonic anhydrase will form carbonic acid, H2CO3, which then dissociates into hydrogen ions and bicarbonate ions. And then we've got this chloride shift when the bicarbonate moves out of the red cell into the plasma and the chloride ion moves in to balance the charges. Okay, here's this picture. This is another key diagram. So we actually looked at this before, but let's look again. We've seen how oxygen is transported in our previous video, but now let's look at how CO2 is transported. Now remember that the tissues are producing the CO2, so CO2 will then dissolve or diffuse. Oops, I didn't want to do that. It'll diffuse into the capillary and into the blood, and CO2 will then remember, it can be carried in a number of different ways. It can bind to hemoglobin, forming carbaminohemoglobin. It can join with water to form carbonic acid, which remember will break off and dissociate into hydrogen ions and bicarbonate ions, and then we said that the bicarbonate will go out into the plasma. The chloride ion comes in. That's our chloride shift. Happens in the lungs, in the tissues. This is the systemic capillary right here. This is the tissue capillary. Chloride shift happens, and then the blood is then going to travel back to the heart. It's going to go to the lungs. Here we are at the pulmonary capillary, and let's look at what happens. Our CO2, remember, is carried. Some of it's in the form of this bicarbonate ion in the plasma, just like we left it here. There it is. It's going to come back into the cell. The chloride ion is going to go out, so the bicarbonate can join back with the hydrogen ion and form carbonic acid, which will then be broken down into water and CO2 gas. The CO2 gas will then diffuse out of the blood cell, out of the red blood cell, and through the plasma and into the alveolus. Remember, because we've got a difference in CO2 levels between the air and the blood. So the CO2 is going to diffuse out. But at first, again, it has to come, this bicarbonate ion is then going to be taken in and moved back through so that it goes through this equation, and the CO2 is then released back into the alveolus. We've also got the carbaminohemoglobin that we had formed back here in the systemic capillary. Again, this is going to let go of its CO2. CO2 is going to be released back into the alveolus out there to breathe it out, and then any dissolved CO2 again can also be diffused back out into the alveolus. So this is how CO2 is picked up from the tissues. It's picked up in your tissue capillaries, and then it travels through your body, goes to your lungs, and then it is delivered and removed then back into the it goes into the alveolus and you breathe it out. All right, so let's look at this question. In the tissues, let's see what of these are true. CO2 is picked up and carried 3 ways in preparation for release in the lungs. Okay, that looks pretty good to me. B, O2 is oxygen is released from hemoglobin, which has a low affinity for oxygen at tissue pH. That means it's more acidic, because tissue pH is more acidic. Oxygen is released from hemoglobin, which has a low affinity for oxygen. Well, let's think about this. Let's read this next one. Oxygen is released from hemoglobin, which has a high affinity for oxygen at tissue pH. Well, these both can't be true, can they? So what we have to go back and remember that hemoglobin has a low affinity for oxygen at tissue pH, which happens to be more acidic. Therefore, it wants to release oxygen at the tissues. So A and B have to be true. So the answer should be D there. All right, let's look at this question regarding CO2 release at the lungs. Let's choose the true statement. Okay, and let's, just for fun, you might want to go back and look at CO2 release at the lungs. This is going to be this picture, and it's going to be looking at these little reactions that we just looked at. Bicarbonates enter the red cell, join with H+, forms H2CO3, which breaks down to water and CO2, which is then the CO2 is released into the alveoli. That looks pretty good. CO2 is released from hemoglobin in the red cell and from the plasma into the alveoli. That looks pretty good. CO2 is released when HCO3 enters the red cell. In other words, it's a reverse of the chloride shift, and that's right too. So in fact, all of these are true. You might want to go back and look at these and make sure you understand that question. Okay, I think that I believe we're going to stop right here for this little video, and we'll make this one won't be quite as long as the previous one. So we'll move into respiratory acidosis and alkalosis next. Thanks.